Okay, last thing in this unit is efficiency. Okay, and efficiency, very simply, is how much of the input energy that goes into doing a job or into a system actually does useful work. Okay, whatever, the higher that percentage is, obviously then the more efficient that system or process or whatever is. Okay, so the initial energy source is the energy input. Okay, the desired energy or useful work is the useful energy output, okay, or work. So we would have efficiency as a formula, okay, looking like this. Efficiency will equal, okay, our useful work divided by our input energy. Sometimes we have EM, okay, written up top, but I'm going to say work, okay, because that's the obvious thing. The useful work that actually gets done divided by the amount of energy we had to put in to actually do it, because lots of it's going to be lost, okay, and that's going to give you your percent efficiency as a decimal, okay, not as an actual percentage. You would have to multiply by 100 to get the actual percentage. So when you do this, if you had something that was operating at 45% efficiency, you would get decimal 45 as your answer. That would mean that process is 45% efficient. Okay, everybody follow me there? So it's exactly the same way you calculate a percentage on a quiz or a test or something like that. Okay, you divide what you got by the total number of marks you could have got, and there's your percentage. Okay, so it's the same for efficiency. Everybody all right with that idea? Okay, that's really the extent to which you need to understand efficiency. Okay, we're going to look at doing a little bit of calculating, but that's a pretty easy formula to use because it's like V equals D over T. Okay, it's just a 3-variable formula. Okay, now, how efficient would you accept something to be, do you think? Like if you wanted to, if you had a process that you had to do or use on a daily basis, how efficient would you want it to be?
At least 70%.
At least 70%? I'd say at least 70%. Okay? I mean, or think about it this way. Would you go to a doctor who was only right 70% of the time? I mean, they're human, they make mistakes, but I'm pretty sure I'd want the guy who 10 times out of 10 knows what an appendix is if he's taking out my appendix. Okay? I don't want him to remove something else, okay, because he's only right 7 out of 10 times. Okay? I mean, again, that's kind of a fake example, but okay, we want something that's going to work pretty efficiently. Problem is, mechanical energy conversions that we use every single day are notoriously inefficient. Okay? Especially anything that tries to turn heat into mechanical energy. That process, that transformation, is inherently inefficient. And it's what we use to get to school and to work every single day. Okay? An internal combustion engine converts heat into mechanical energy. And it does so quite inefficiently. Okay? So, if we're just looking at examples of different kinds of vehicles. Okay? So, if for a truly just a pure gasoline vehicle, which is probably what most of us drive, okay, your engine losses, so if we're talking 100% of the energy that's in the gasoline you put in the car, 68 to 72% of it, that's more than 2/3, is lost and doesn't do any useful work, most of it as heat. So thermal engine loss, like the radiator, exhaust heat, etc. Okay, so you've got heat and combustion, pumping, okay, and friction, okay, and then exhaust heat, etc. 58 to 62% of the energy in your fuel is radiated away from the car as heat. Okay, in order to properly radiate that heat away so that it does not destroy your vehicle, you have a cooling system that consists of a water pump, coolant, and a radiator. Okay, are you guys familiar with these parts? Okay, especially this time of year, sometimes you can hear people's water pumps. It's a horrible squealing sound. Okay, if it's not working right, okay, it sounds like a terrible squealing sound. Okay, so that has to run, and it takes energy from the motor, mechanical energy, to turn the pump. There's actually a belt that comes off of the drive shaft that turns your water pump, and your alternator. Your alternator is the thing that generates electricity and runs all the electrical parts of your car. Okay, so those two devices actually steal mechanical energy that doesn't drive your car forward, okay, but is necessary to keep the car from melting down and destroying itself. Okay, so 68 to 72% is engine loss, not driving the car forward. Okay, auxiliary electrical losses, 0 to 2%. So that would be the climate control fans. Okay, so this time of year you get in the car and the first thing you do is crank the heat and the defrost and the fan blows like crazy. Okay, so you got that. If you have any seat warmers, or if you're really lucky, you got the heated steering wheel. Anyone got one of those? My wife had a loaner and it had a heated steering wheel. Oh man, that was so cool. Okay, but yeah, like especially this time of year. But it takes electricity. It's a small little electrical heating element that runs through the steering wheel. Okay, it takes electricity. Headlights, power windows, power door locks. Okay, if you've got the the display. Okay, if you've got the touch screen in your car, that's electrical. All of that stuff, okay, takes electricity. If you've got the big stereo, okay, you're that guy. The rolling rave that goes by my house. It's that guy. I don't know if he goes by your house too, but okay, he goes by my house all the time, right? His stereo probably ups that percentage to more like 5% because he's probably got 3 amplifiers that are all drawing power, okay, away from his car, right? In fact, we used to have a car show kind of thing at the school years and years ago, and one guy had this car, and it was like a 1998 Fox body Mustang, 4-cylinder. He called it his Rustang. You can imagine why. Okay, and he had this huge stereo. The whole hatch of it was filled with subs. Okay, and he had like 4 amplifiers hooked to the thing to power the subs. Okay, he was the rolling rave guy. You could hear him from 10 miles away. Okay, and what he would do is he would pop a loonie onto the top of the car, and then he would crank the stereo, and the loonie would dance. It would bounce on the top of the car. And I don't mean like this much. It would bounce like this much from the vibration of the stereo. Okay? But he had to actually put in a second alternator, a second electrical generator that stole more power from the engine in order to power the stereo. $2,000 car with $10,000 worth of stereo equipment in it. Okay? And then one day he cracked the back window with the stereo. It was pretty cool. At least that was his reaction. I watched it happen, and then I looking at him and I'm thinking, oh man, he's gonna freak out. That's the window that's got the defogger in it. It's really expensive to replace. And he just looked at it, he's like, cool. It's like, wow, you're really chill. Yeah. Okay, so all of that stuff, all the electrical stuff takes energy away. That's not driving the car forward. Parasitic losses. Okay, this is like friction, internal friction, things like that. Water, fuel, oil pumps, ignition systems, engine control systems, all the pollution control stuff, another 4 to 6%. Okay, drivetrain losses, okay, 3 to 5%. Idle losses, so when you're just sitting there idling at a stoplight, okay, if you don't have like the auto shut off, most modern cars now have that engine thing that kills the engine if you're just sitting at a stoplight. Okay, so that reduces it. Energy to the wheels, 16 to 25%. Okay, so in an average gasoline-powered vehicle only, okay, 16 to 25%. So if you're on the higher end of that, you might get 1/4 of the energy in your gasoline actually powering the car forward. Okay, so that means you put $100 worth of gas in your car, only 25% of it actually does anything good. Okay, actually powers the car forwards. That's how inefficient it can be. Okay, now if you have a hybrid vehicle, your efficiency goes up because you have an electric motor that assists the gasoline motor. Okay, so your car consumes the most gasoline when it's accelerating, when it's actually having to do a lot of mechanical work and accelerate the car and change its kinetic energy. Okay, that's when it consumes the most fuel. So in a hybrid vehicle, that's when the electrical engine will kick in. Okay, so you've got your internal combustion engine, and then you have an electric motor beside it. Okay, when your car is under heavy load, it will activate the electric motor to assist the gas motor, so the gas motor doesn't have to work as hard and doesn't burn as much fuel. Okay, that makes them more efficient. Okay? So if we're looking at engine losses, we're down to 65 to 69% from 68 to 72%. Okay? Parasitic losses, about the same, 4 to 6%. Okay? Auxiliary electrical losses, about the same, 0 to 3. There's going to be more electrical losses in a hybrid vehicle because more things actually run electrically. Okay? Drivetrain losses, about the same, 3 to 5%. Okay? Energy to the wheels, 24 to 38. Is that a significant improvement? It is. Okay? Electrical engines are far more efficient because they're converting electrical energy into mechanical energy, not heat into mechanical energy. Okay? So they work more efficiently. And in most hybrid vehicles, you also have something called regenerative braking. Okay? Which means there's those thermocouples in the brakes that we talked about on like the first day of the unit. When you apply the brakes, the heat gets turned back into electricity, okay? And it goes back into the battery, so it's free. Okay? We just recently got a plug-in hybrid vehicle ourselves for our family, and it's teaching me how to brake efficiently to maximize the energy return. It actually gives me a score on the little screen beside the speedometer every time I stop. And it's like a game now, okay, that I have to get 100%. Okay, each and every time. So it actually can train you to brake efficiently, okay, instead of what I usually do, which is drive aggressively and and slam on the brakes when I have to. Okay, it's now I brake from further away and I get more of that regenerative braking energy going back into the batteries. Okay, so all of that makes it quite a bit more efficient, which means in the end, you're going to have less gasoline to put in. Okay, ours is actually also a plug-in hybrid, so we can actually plug it in and drive it all electric for about 25 to 50 kilometers, okay, if we're lucky. All right, so energy to the wheels, okay, yeah, you got 24 to 38 here, okay, you got some wind resistance losses, but you have that in all cars, okay, rolling resistance, that again, you have that in all cars, and then braking, well, the braking actually gets used in this car to do something good, okay. Everybody follow me there? What do you suppose happens to those numbers if you go to an all-electric vehicle? Yeah, they go up even more, because again, the inefficiency is in the internal combustion engine that's converting heat to mechanical energy. Okay? So any systems that have moving parts are always going to lose energy as heat. That's kind of the big deal with things like that. Okay? And so that's because of the second law of thermodynamics. Heat goes from hot to cold, so it's always naturally going to bleed away from your car, okay? And go to other places. So as we said, this is how we calculate efficiency. Okay? Some machines or systems involve conversion of mechanical energy to another form, but if we're looking at an electric car, okay, suddenly these numbers change considerably. Okay? Energy lost in charging the battery, 10%. Okay? There's always going to be some heat generated when you're charging the battery. It's going to be about 10%. Accessory losses are still about the same, about 3%. Electric drive system losses, 18%. That's down from 68 to 72. Okay, so it's considerably less. Okay, you've got a lot of, you've got 4% auxiliary losses, but look at this, 65 to 69% energy to the wheels. That's like the flip of an internal combustion engine. It's the other way in an internal combustion engine. Then you've got your regenerative braking, which is going to add another 22% back to the battery, okay, which can be used again, right? Making it 87 to 91%. Efficient. Okay, I'm not saying go out and buy a Tesla or some other electric vehicle. Okay, this is not like I'm from Greenpeace and I'm telling you you're terrible for driving an internal combustion engine. I drive a V8 powered truck. Okay, I'm not going to be a hypocrite here. Okay, and say you need to go out and buy an electric vehicle. Okay, but I am saying that the truth is they are more efficient. Okay, do they have drawbacks? What's the drawback of an electric vehicle? Right, range. Okay, if my internal combustion engine gets low on fuel, I just pull over and take well, it's my truck, it's more like 9 or 10 minutes because it's really thirsty. Okay, but I have to fill it up with gas and then get right back on the road. Can I do that with an electric car? No. Okay, and an electric car, if you got a really good one, you might be able to go about 600 kilometers on a charge, and then you got to stop, and you got to wait a few hours while it charges up. Okay, whereas in my V8 powered truck, I can go 1,100 kilometers on the giant 137 liter tank that it has. I don't enjoy that when I'm watching the number of the dollars that go into it when I fill it up, okay? But it certainly can go further, and I can just fill it up and keep going, okay? That's certainly the advantage, okay? Around here, why do we see so many Teslas? Anybody know why there's so many around here? How far do most people drive to work around here? In Okotoks, more than 2/3 of the population drives into Calgary for work every day. Into Calgary and back is not 600 kilometers. Okay? And electric cars are great in stop and go traffic. Okay? So they're perfectly set up for this type of suburban living. Okay? They're a great system. Plus in Okotoks, our town council decided that if you have an electric car, you can plug it in for free. For now. I'm sure that won't always stay that way. Okay, but you've probably seen like down in front of town hall, down in front of the library, right? There's those electric car charging stations in Okotoks. Those are free. Okay, you can plug in and charge your car for free, which used to annoy the heck out of me until I got a plug-in hybrid car and said, don't hate the player, hate the game. Now I plug in for free too, okay? And I get free gas. But yeah, it won't be that way forever. Okay, but it is more efficient. Okay? There's certainly still drawbacks to an electric car. Okay? They don't have the range, certainly. Okay? But other than that, really, they are a lot more efficient, and electricity is going to be cheaper than filling it up with gas. Okay? Problem being, electric cars tend to be kind of expensive, at least initially. But you can make that back if you can plug it in and it's running more efficiently. So things to think about, but that's where efficiency is very evident in our daily lives. Okay? We accept incredibly poor efficiency to get ourselves anywhere all the time. Imagine the efficiency of a school bus. Okay? These are all small cars that we were looking at. Imagine how inefficient the diesel engine in a bus is. Okay? Now granted, it's going to carry 30 people, that's its advantage, but okay? It's certainly not going to be the most fuel efficient vehicle in the world. Okay, let's have a look at this example here. So I think this one is in the notes, okay? If you don't have your notes package, maybe just take a quick minute here and write it down, and we'll just walk through the calculation here in a second. Okay, so with this problem here, and obviously we got the solution, but it's kind of hard to read the way I've written it here. So we have a crane that's lifting a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.3 times 10 to the 4 joules of work, or mechanical energy input. So that means it uses that much energy. 2.3 times 10 to the 4 is 23,000 joules. Okay? It only does 8.00 times 10 to the 3 joules of useful work. That's 8,000 joules. Okay? What's the efficiency of the crane? Okay, well, efficiency, okay, is our work divided by the energy required to do it. 8,000 divided by 23,000. Okay, so we get what, 30.348? Is that what it comes out to? I think so, 348. And then there's no units on that because it's a percentage. Okay, you could write 34.8%, and that would also be correct. Okay, everyone follow me on how that formula works? Okay, not too difficult, right? Okay, so the main thing here that you guys have to understand, because I actually didn't put any efficiency calculations on the test, okay, is what efficiency is, how it's applied, okay, things like that. It's more in the multiple choice. Okay, so if that's the way it's going to be tested, let's think about some other places where we might be looking to improve efficiency. What are some things you can do in your house to make it more efficient? What kind of light bulbs do you guys have in your house? Yeah, okay. You can get, there's 3 different kinds of light bulbs. the original Thomas Edison tungsten filament, okay, incandescent light bulb, okay? Then there's compact fluorescent, those are the glass coil ones, okay? You don't see those much anymore, okay? And then there's LED, which is probably the most common type that we would see now, okay? Well, back a few years ago, the government actually put out a thing where you could submit your receipts for replacing all of your tungsten filament light bulbs in your house with LEDs, because it wasn't cheap. If you had a decent sized house, you'd be replacing probably 30 to 50 bulbs, okay, in your house, okay, and at a couple of bucks each, it added up. But it significantly reduced the amount of energy your house consumed. Okay? If you have one of the Thomas Edison style, that's not good. Okay, there we go. Okay, if you have one of the Thomas Edison style ones, right? So right, that have the filament inside like this, okay? If you have a standard one, it's 60 watts, okay? A watt is a joule per second, okay? So this light bulb uses 60 joules of electricity every second in order to light your house. And the reason it does that is because this coil is made of tungsten, which is highly resistant to the flow of electricity. And it gets super hot. And because it gets super hot, it glows and puts out light. That's what incandescent means, glows and makes light with heat. Okay, so 60 joules of energy per second. Okay, you could replace that with one of the compact fluorescent ones, which, like I said, and this is going to really test my artistic ability, kind of look like a spring. Okay, just a coil of fluorescent bulb. Okay, you could replace a 60 watt bulb with a 13 watt compact fluorescent bulb, which cut your electricity costs by 75%. Okay? Or you could replace it with an LED bulb, which looks just like this, except it doesn't have the coil inside of it. It's got just a bunch of tiny little light emitting diodes, and that can be replaced with a 6 watt LED bulb. Okay? When we first did this in our house, our electricity bill went down significantly, okay? And it was just because of the lights, okay? All we did was replace the light bulbs. They were consuming so much electricity. We reduced it down to 10% of what it used to be, okay? Just by replacing the light bulbs in our house, which is good for our electrical grid, and it was good for the environment because then the coal-fired electrical plants weren't using as much coal because everybody's houses were using more efficient light, okay? Are there other things you can do in your house to make it more efficient? Where does your house, do you suppose, lose the most heat?
This,
Well, your furnace is what makes the heat. Yeah, but I mean, like, what part of the house would allow heat out the most easily? How many of you sit over there in the morning when people are coming in and out? You ever notice how cold it gets when the door's open? Okay? Think about your door, okay? Think about the walls of your house. The walls of your house, okay, are about this thick. Your door is about that thick. Okay? You lose a lot of energy out your door. What about your windows? They're even thinner. Okay? Now, you can get different kinds of windows. Okay? That's a place where you can get more efficient. Okay? You could actually put in what are called triple pane windows, which actually have 3 panes of glass, and in between the panes of glass is argon, okay, which is just a gas but doesn't transmit heat very well. Okay? Makes them more efficient. You could get a better insulated door, okay, or a door that doesn't have a window. And if your door has a window, it's probably only a single pane of glass, okay, and that's going to let a lot of heat out. All right? Or maybe your door doesn't seal very well. You can put one of those draft snakes, okay, at the bottom of the door, right, so that heat doesn't get out through the bottom of the door. There's all kinds of things you can do, okay, around your house that can increase the efficiency and lower your utility bills. That's probably not a concern for you because you probably don't have to pay your utility bills yet, but one day you will. Okay? And then you'll want to do everything you possibly can to lower those utility bills. Okay? Like, you know, not leaving your lights on. Because the light switch operates in both the on and off positions. True story. Okay, making sense? This whole idea of efficiency? Okay. That's all you need to know about efficiency. Now, we didn't get a lot of time to do review on Friday. I basically just got through doing the review. If there are any questions from the review package, I would gladly answer those right now if anybody had any. If there aren't any, I would suggest that the last 50 minutes of class could be used to work on, well, I don't know, the review package, since you have a test tomorrow. And then if any questions come up, you can ask, and I will answer them. Okay, so let's do that.